Thanks for your interest in this talk. My name is Michael. I'm the author of GREMLIN Scala. I work at Shift Left, and we do static code analysis using graph databases to do useful things like finding security vulnerabilities or finding data leaks, and so on. We love open source, including the giving back part, and we are hiring. So if you're interested in any of what follows and you like open source, please get in touch. Yeah. So basically, in this talk, I'm firstly going to go over what a graph database is and where the differences are to relational DBs, what they are when you might want to use them. Then I'm going to go over a few query languages that you can use to actually write your traversals or queries to get some data or information out of the graph. And then the main part is going to be on GREMLIN Scala that allows you to write your queries in a type-safe way and how you can do that. Okay, so when I first learned about databases, this is probably what you saw. So this is an example of a concrete DB. It's a relational database. So you have tables, and in this case, the scenario I'm going to use across the talk is a person might like a pizza or two, and basically you in a relational DB you put into three different tables. You have a person table where every row corresponds to a person. Then you have the likes table because it's a many-to-many relationship, so one person can like many pizzas. And then you've got the pizzas, and they have names and attributes and whatnot. So you have like rows and columns and that. It's by far the most popular model, and there's a reason for it. Lots of funding went into it, lots of research, and it's just the most popular one. And everybody knows SQL. The tools are highly optimized. The databases are very mature. They're better tested. Great tooling. So there's lots of reasons to use relational DBs like Postgres and MySQL and so on. The point I would like to make, though, is they also have some downsides. So interestingly, most of the downsides are about when it comes to relations, because relational DBs are actually quite bad at handling relations. So if you have a look at that schema here, and you wanna write your SQL to find me all the pizzas that Alice likes. What we need to do is we need to join these three tables together, and the SQL looks like this. So you don't need to read every word here, but basically what I'm saying is for a simple task like find me all the pizzas that Alice likes, in SQL, this gets quite long, quite ugly very, very soon. In comparison, if you write the same thing in Gremlin, which is a graph traversal API that I'm going to talk more about later, it's very natural. It's very easy to read that, even though you probably haven't seen any Gremlin before. So it's not only so if you then go one step further and you wanna say, well, let's get some pizza recommendations. So basically, find me all the pizzas that Alice likes, and then find the people who like the same pizzas, and find the pizzas that they like. This just explodes. Right. So it's a bit ugly when it comes to relations. It can also get slow. So because every time you do a join, you need to look up something in a global index. So the complexity is log n basically. So it grows, the time that it takes for that join grows with the size of your index. So basically the size of your data set. Whereas typically in a graph DB, you have a node-centric index. So the index, the node itself, the vertex itself, has the pointers to the adjacent vertices. I'm going to define what vertices are in a second. Also, typically in a relational DB, you need to define your schema up front, so it's not so great for doing some prototyping and so on. Which typically in a graph DB is optional, so you don't have to. With a relational DB, you always have the juggle between normalization, so how clean is my schema, which typically leads to many tables, versus how much they optimize for performance, which typically leads to wide rows, which might be sparse then as well. So this constant juggle that you always have to keep in your head. And my last bashing point is the object relational impedance mismatch. So that basically just is a fancy term for if you have if you're mapping your table to a class, and your class has a list property, then you need to store it in a separate table, and then join that back in when you hold it. So most of you might have had that fight with your object relational mapping framework and so on. So those are all reasons for where relational DBs have some downsides. Again, you should use them in 98% of the case because they are just so much more mature. Anyway, this talk is about graph DBs. So some propaganda. Most propaganda is free, and so is this one. So that's from a book called Graph Databases from O'Reilly. It's written by the Neo4j guys. So it's like the apparently most popular one around. But yeah, it's certainly propaganda, but there's some truth to it. So they're comparing finding the friends of friends. So like in a social network, friends are friends, and they have friends, and they have friends. So if you go to depth 2, so depth 2 is just friends of friends, right? Then it's about the same size. If you can't read those numbers, so it's basically 1 millisecond in this use case in this setup. What they did is they set up a DB with 1 million people and 50 friend relationships per person on average, and they basically just execute that current compared to time. And the main point to see here is in Neo4j, which is what they're advertising here, the times grow with a constant factor, whereas in a relational DB it grows exponentially. The times to do these lookups. Now again, careful propaganda. Obviously, there's ways around that if you do this with a relational DB. So yeah, you can set up certain things and pre-compute certain things, which to make this more pleasant in a relational DB. But the main point is, with the graph DB, you get this for free. Basically, that's the whole point of a graph DB, is that you can look up these relationships with constant time, so super fast compared to log n. Okay, so I talked a little about graph, but what do I actually mean by graph? So actually, what I mean is called a directed property graph. So it's directed. Well, let's start with a vertices. I've used that verb a few times now. Noun a few times. So vertices are nodes, or you might just say things, and they can have connections. Those connections are called edges, each of which have an ID, exactly one ID, just like in a relational DB, you would typically set an ID, or the DB would set it for you, and they have exactly one label. So that's basically like in your table name in a relational DB, and they have 0 to n properties. So nodes can have 0 to n properties, and edges can have 0 to n properties. I'm going to use this this sample for the rest of the talk, basically. So I'm just going to go over it. So we have a person, Alice, with a name Alice, and and she's got an age, and she likes pizza tonno with a weight 3, and pizza romana with a weight 5. So she prefers that one, but she likes both. So basically graph DBs are quite good for defining these ad hoc relationships and looking them up and so on. So for anything that's highly relational, don't look at relational databases, but you may want to consider a graph DB with those caveats that I mentioned before. So here's one use case. We're not going to go into every detail here, but basically that's the domain that we're in at Shift-Left, where we basically pass source code into its atomic elements, and we basically have things like declarations and functions and operators as our elements, and then we put edges on top of that, so to model things like the control flow graph and the data flow graph. And with that, if you then try and find connected things, like for example, you have an HTTP input that you might get a password from your user, and you find a connection where that password goes into some string and doesn't go through some sanitization methods and goes straight to a log file, like we just recently had with Twitter, we can detect that kind of stuff, right? So that's the idea. We're finding things in the graph by traversing it. Right. Okay, so there was a quick definition of what a graph is and why you might want to consider it. If you do want to go for it, then there's a few options with when it comes to query languages. So I'm gonna basically name 3, and then I'm gonna zoom into the third one. So Cypher. Cypher was originally created by Neo4j for their graph database. It's one of the longest ones around. They're very popular, like the popular one, the most popular one. They've open sourced Cypher as an open Cypher effort, and some other vendors adopted that. It's a declarative language, so the idea is you write your traversal just like you would draw it on a piece of paper. So that's really nice. I'm not really an expert on it, so I can't really judge. Like, there's certainly use cases where it's great for, and some that it's not so great for. But since this talk is about type safety, so I had a look at libraries out there for Scala and how that let you write your queries. And I found 2 that were sort of popular, and one was for SPARQL, the other one was for ANORM, so the play framework, and they both help you with the scaffolding for these specific tools. But when it came to writing your traversals, you still had to just do it in a string, right? So you basically write this in a literal string, and that's all. So you don't get any, as far as I could see, you don't get any type safety from that. So it's not so interesting for this talk. SPARQL. I only learned over lunch that it's called SPARQL and not SPARQL. So I'm certainly not an expert on SPARQL, but it's basically it's a W3C language. So you see their love for XML namespaces here. It looks a bit like SQL. It's also a declarative language, and they have this select statement that selects tabular data. They also have a I think it's called create, that basically creates a subgraph. But the point is, SPARQL is for RDFs. RDFs are triple stores, so they're like the most low-level primitive for storing data that you could imagine. It's always subject, predicate, object. So Alice likes pizza. And yeah, so that's a triple. You can't do more than that. Or Alice has ID 1. That's a triple. So lots of triples, and the idea is those are so primitive that you can then build your own ontologies on top of that, and then invent your own languages to query it on top of that. Again, I looked for libraries to express this kind of stuff in a type-safe way. And yeah, I found one for, again, specific for Spark, but again, it was just the scaffolding, not so much writing the queries in a type-safe way. So again, that didn't really help much. Yeah, it seems to be mostly used in academic environments, but yeah, not quite sure. Third one, and then I'm gonna zoom into this one for the rest of the talk. Basically, GREMLIN. So it's the idea is TINKERPOP tries to be the JDBC. What JDBC is for relational DBs, TINKERPOP tries to do that for graph databases. That's the mission statement, so to say. This is GREMLIN Groovy, which is the main style, and basically it's imperative. So you have lots of steps that you can combine, and they compose. There's a declarative style available as well, but this is certainly the main style. It's a Turing-complete language, if that matters to anyone. There's a long list of DBs that implement this API, local as well as remote. So basically, you write your traversal like this, and then it executes if you have a local, like in memory or backed by a local file system database, or if you send it to a remote DB, it's the same API. The the maturity of those DB drivers varies a lot, so that's something to keep in mind. There's many libraries for different host languages. So this is Gremlin Groovy. There's Gremlin Java, which is like the underlying one, and there's Gremlin Scala, which we're gonna zoom into, and then there's Python and JSON, JavaScript and .NET, and yeah, I think some more. Okay, zooming into Gremlin Scala. So it's basically a wrapper around Gremlin Java. And the main objective is to give you Scala-friendly function syntax when you define your traversal, and not just traversal. I'm gonna show a few other things, like if you want to add vertices and edges to your graph. And not just the function syntax, but also to make it type safe. So make use of Scala's advanced compiler and type system to help you in your IDE by deriving some types for you that otherwise you would have to cast or just do some guessworks. And also prevent some families of illegal queries for you at compile time rather than erroring at runtime. And yeah, Scala is a great language for embedding a DSL, as you will see. And the main thing is it's just a thin wrapper on top of Gremlin Java. So if anything is missing, or there's probably a few things missing, you can always go back to the Gremlin Java. Getting some setup out of the way. So basically, the next few slides all assume that we have this wildcard import of Gremlin Scala, and we have some instance of a graph. Right, so that's TinkerGraph is an in-memory like the reference implementation of a graph, and this could be anything else. This could be a Janus graph reference or a reference to a Cosmos graph or whatnot. There's a project. I think I have a link on the last slide, Gremlin Scala examples, that helps you with the setup of different graph DBs. So there's like 5 or 6 different DBs that you have the setup for. Cool. So when it comes to type safety, what we basically need to do is we define our schema once, and then we use it everywhere. So that's the slide where we define our schema. In practice, what we do, for example, is we have a JSON file where we actually have our domain-specific schema, and we generate lots of stuff out of that. So this kind of code could be generated, or you read it, whatever. So for the given schema that we had before. We define person nodes as they have a label of type person. That's got nothing to do with type safety. That's just it's just a string. The second one, the name. So we basically say a person has a name property with a type string. That's all that is. And again has an age property with a type int, and those like edges have also one property with a name how much, and it's of type double. The idea is, you define it here, you use that everywhere, and then the compiler can infer those types for you. And I'm going to show you what that means. So first, before we do any traversals, we have some, this is the syntax to actually add vertices, or this is one way to add vertices and edges to your graph. So the first 2 lines basically add 2 nodes. So they add the Alice person node and the Pizza Tonno node, and they set some properties. And because we already use our name and age keys here, there's already some type safety that you get here. Because, for example, you couldn't say age is some string, because it has to be of type int. So this is when you add your nodes. And then the lines below, they actually create some edges between those nodes. So as soon as those lines execute, you will have those edges. The first one just with the label. So Alice likes Tonno, and the second one you can provide a tuple to also set some properties. This was a user contribution and made me realize how cool Scala is to embed your own DSL into it, because I think it's quite nicely readable. The other way to add vertices, for example, is using case classes. So there's a black box macro in here. This, by the way, is the only macro in Gremlin Scala. where in this case we have a case class person with an ID, which is optional because it's being set by the DB, and then we have the two properties that we had before, so a name, and in this case I made the age optional, and then we can just add it to the graph by saying graph plus an instance of that person, and when what we get back is an instance of vertex, and we can convert that back to an instance of the person, and then the ID property will be set in this case. So bear in mind that macro has some rough edges. It works for these simple cases, but yeah, it's certainly not bug free. There's lots of issues around it, some rough edges. But if you have some simple thing, you can use that kind of stuff. I was about to rewrite that in Scala Meta and Scala macros, but yeah, it's stalled a little bit because the directions are a bit unclear when it comes to macros. Okay, so I was talking about traversals. So traversals are basically you want to get some information from the graph. So just as a convention, we use G as the traversal source. So we can start any arbitrary traversal with a G, and we get that G with just graph.traversal, just some convention in the TINKERPOP universe, and then what we can do is G.V. V stands for vertices, right? As opposed to E for edges. So the first thing to bear in mind here is traversals are lazy. So G.V, the return term is Gremlin Scala, and Gremlin Scala of vertex, because the end type is a vertex. We're on a vertex. In this case, all the vertices. But the first line here in the second block doesn't actually do anything yet. It's just defining the traversal. If you then run to list on it, you get back a list of vertices, and that's when it actually executes. So the middle box will give you all the vertices in the graph if that's really what you want. Oftentimes you just want to start your traversal with a single vertex or single edge or whatever, and then you just specify for example, you could specify the ID of that vertex, and then again, you just so in the third block, V1 is that just returns the Gremlin Scala of vertex, and if you then run head option, then you get an option of vertex. Okay, so now if we started some simple vertex, so say V1 is Alice. If we want to find out what pizzas she likes, we just say out likes. So out means follow all the outgoing edges to the adjacent vertices, so to the next vertices. And to be more precise, out is actually a short form of out_e.inv. So what this means is we follow the outgoing edges. In this case, we could filter on the edges. We could say only give me the ones that have a how much property of at least 4. And then follow the incoming vertex. And then previously on when I talked about joints and how complex it would be to get some recommendations, I mentioned this example, pizza recommendations. So here we just say, well, start with Alice. We know her ID. Find me all the pizzas that she likes. Find me all the people who also like the same pizzas, and then find me all the pizzas that these people like, right? So in a SQL, if you write this in SQL, this basically wouldn't fit on a slide, and this is, I think, quite straightforward. So that's sort of if you're in such a domain, then these query languages might be better than SQL. Like I said, you can concatenate lots of steps. So I'm going to show you a few of the most basic steps. There's about 20 or 30 or so of them in total. So one is the hash step. So we can say find me all the vertices that have a given label. So that's basically like you can imagine that like select star from some table name. Find me all the vertices that have a given property set. So everything that has the name property set. So in this case, we will get all the vertices because person as well as pizza has the name property set. Or, and now it's back to type safety, you can say, find me all the vertices that have the age property set to a value between 25 and 35. Type safety, because if you type this in your IDE and you say p.between, and then you get the autocomplete, you know at that point that you have to provide 2 integers, because we defined age as a key of int. So you can't provide anything other than integers there, and so yeah, compiler errors otherwise, and you get some IDE help. Right. You can do group bys. So first box would be give me all the vertices and group them by their label. So that's basically like saying, well, list me all the tables out there. And what you get back is GREMLIN Scala, because it's lazy, and if you execute head on it, you get a map of string to collection of vertex. So that's basically the key of the map is the label name, and the collection of vertex is all the vertices that are that have that label. But you can group by arbitrary things. So second box is group by __ out count. So __ is similar to the underscore in Scala. It's an anonymous traversal, and basically, if you just look at that anonymous traversal, so say _out count, that's the degree of the vertex. So how many outgoing edges does this vertex have? So I'm grouping all the vertices by their degree. So this is to find. Then I would say. At the end, I don't know, limit 10 and give me the 10 super nodes in my graph. So if I have some very highly connected nodes, they have special properties. Find me those, for example. Third one, do group count by the age. So find me all the vertices that have the age property set, and do group count by that specific property. And again, because we defined the age as a key of int before in our schema, we get back a map of int to long. So the key is the int, because that's the age property. Repeat step. So I think the first one's pretty obvious. So we start at a specific vertex, and we repeat an arbitrary traversal. In this case, we follow all the outgoing edges to their adjacent vertices, and we do that 3 times. Second one, a bit more useful. We do that repeat step of following the outgoing edges to the adjacent vertices, and we do that until some condition is met, and that condition can be an arbitrary traversal again. In this case, if you just see the last line, out count is 0. So basically, this means follow all the outgoing edges to the adjacent vertices until we're at the border of the graph. So we've discovered the frontier of the graph. So the outermost nodes in the graph. But yeah, this could be it's just an example. Could be anything. We also have select. So typically, if you write your traversal, you get back the last thing in your traversal. So in the examples before, I don't know, we looked at some property or so. But sometimes you're interested in more things along the way. So to do that, what you can do is you can label your steps on the way. So in this traversal, if we ignore the S steps for one, so we started, or in this case all vertices, but let's say some specific vertex. We follow the outgoing edges, and we look up the value of how much. So how much does a person like a pizza? If you wouldn't have the select, then you would get back a list of doubles. So a list of how much do people like pizza, but you have no idea of who likes what, how much. So if you label them, so you say with the vertices, you name them something, you give it some label, maybe more meaningful than A, and then you at the outgoing edges, give them a label as well, and then you look up some value and do whatever, and at the end you just say select, and in this case, the return type is not of type double, but is of type tuple. So in this tuple contains all the elements that you've labeled, all the steps that you've labeled with their concrete type. So in Gremlin Java or Gremlin Groovy, what you would get back is an array of objects, and you would have to cast your way around. But here we can just use well, this is implemented with shapeless, and it's actually fairly simple by just holding by just storing the labeled members as a type member, which is an H list, and that's how we can preserve the type. So if you run toList on this, you get back a list of the tuple, so a list of vertex H double. Right. Yeah, the other thing I mentioned is you can catch some families of compile time errors, of errors at compile time. So in a dynamic language you don't have any compile time, so you can't get that. But also in Gremlin Java you don't get most of this. So the first one you can't. So you started all the vertices. Sorry. And then you follow the outgoing edges, and then you're on a vertex, and you want to follow the outgoing edges again. But outgoing edges only exist on an edge. On a vertex. So if you're on an edge, there's no thing as an outgoing edge because you only have the vertex that's adjacent. So this you can catch at compile time, and Gremlin Scala does that. Second one would be setting a property. So we define name as a key of string. Hence, we can't set it to an integer. So the compiler tells you, well, you can't do that. So property name value doesn't compile if it's the wrong type. And the third one, we look up from all the vertices. We look up the name property, and we know it's a string. And now we want to compute the mean of those name properties. Well, mean doesn't make any sense for a list of string, so this doesn't compile either because there's no view available from string to number. So it has to be some number, like int or double O. Also, some magic on top. Typically, if you're in some domain, you don't wanna wrestle with, or if you wanna show what you're doing to your domain experts, you don't want to show them Gremlin queries. So instead, what you can do is you can quite easily define your Gremlin queries in your own abstraction, and then name them. So in this case, these two lines, these two boxes are exactly equivalent. So the upper one is your own domain for your domain experts, and they will understand that. So find me all the people with the name Alice who liked something, and they rated it at least 3. So the implementation of that is in the bottom box. So look up the name property, follow the outgoing edges with some filter, must be greater than 3, and then go to the adjacent vertices. The result is the same, but the upper one is much more readable. And so if you want to do this kind of stuff, you can obviously always do that in your own wrapper around Gremlin Scala. But if you use the one that if you use some of the wiring that's there, you get certain benefits. Like you can also do the as select, type safe select, and a few of the other things that I've shown before out of the box, basically. Right. Now, there's obviously some downsides. I mentioned that in the beginning. So, majority of the databases and database drivers far behind relational DBs. So I think there's no comparison in those regards. So the benefits of having a very relational domain and having to do these kind of traversals that are very connected must far outweigh the downsides that you're swallowing here. It is a very rapidly expanding space. So there's a few really good new contenders that just joined the community, and that well, Microsoft and AWS, they've got some implementations now that run on their clouds. There's some open source Janus Graph and Edge-Left. We've also made some modifications to the reference implementation of TINKERPOP, which is just an in-memory DB, and we got some 70% memory, better memory use out of that, and we've open sourced that. So it's rapidly moving, but yeah, it's still far behind. Same goes for the tooling. So yeah, at some point, if you use this kind of stuff, be prepared to actually step in and contribute. So summary. So we talked about graphs. So I think they're fundamentally a much simpler model than relational databases. Relational databases have the wrong name because they're actually not that great for relational domains. They're so graph databases are far less mature. There's like, depending on the use case, for our use case, graph DBs are perfect, and relational DBs would be very bad. Your mileage may vary. It's a very active field, as well as in the open source as in the closed source. There's lots of stuff going on. And we talked about GREMLIN Scala, how you can embed, how nice Scala is for embedding a DSL, and how GREMLIN Scala lets you define your queries in a type-safe way and help you with compile time, rather than having to cast your way around. Right, and that's basically all I have. Thank you.